life, right? Now, so what I'm going to talk with you is the first thing is I am going to introduce you the units that we are using in space, and then I will go step by step to introduce you different methods that we are going to use to measure different distances in astronomy, right? And all of you probably know that if I ask you the distance or the length of your book, you are going to measure it from a smaller ruler, right? And if I am going to ask you a length of a very small, piece of eraser or something like that, very small, objects that you usually use in, laboratories. Most of the time you use something like, the vernier caliper or something like that, right? And also at the same time, if you are going to, measure the distance, let's say from Colombo to Matara, you don't use the same scale, right? So I haven't seen that no one is explaining the distance from Colombo to Matara in terms of millimeters, right? So we don't do it. Right? And you all know obviously uh, why is that, right? So we are using different methods and different units, when you talk about different scales, right? Now, for example, when you take a vernier caliper, assuming that I guess most of you may have a little bit familiar with, at least, have done some A-level physics. So from the vernier caliper, you are going to measure the very tiny distances, like 0.01 millimeters kind of distances. But when you go for the next scale, like a length of a table and length of a book, something like that, you can use a meter ruler or something like that, and you are going to measure it in centimeters, right? And if you are measuring uh, like a length of, if you take a running track, we have like 100-meter racks, 200-meter like that, right? So we use 200-meter. It's in terms of meters, but you are not going to measure uh, the distance from Colombo to Jaffna or Colombo to Matara like that using, let's say, meters or centimeters, right? So mostly what you are using is kilometers. So that's the standard because the distance is larger. So it doesn't make sense to, use millimeters or centimeters, right? So like that, we are going to introduce a completely new set of units in astronomy, uh, which we will be using to measure distances uh, at different stages. And the interesting thing about astronomy is even the method that we are going to measure the distances is different, and you will learn one by one why is that different and how uh, what are the differences that we have in different methods and why we are using those, right? So this is something different compared to what we used to use in our day-to-day life. And if we are so basically I will be introducing you how to measure the distances to nearby planets and how to measure the distances to the nearby stars, and measuring distances to nearby galaxies will be different than any of those. And when you go for further distances like the billions of light years away, the methods that we are going to use to measure distances will be even more different. Like we are going to use something called type 1a supernova, and even further distances we are going to use something called redshift distance, right? And finally, if time permits, I will probably introduce a little bit about this concept about the accelerating universe, which is one of the profound discoveries that we came across in recent last 20 to 30 years, primarily due to the discoveries of these new measurement methods, such as, using type 1 supernova to measure larger distances, right? So let's see how these things work. And before I start, since I am going to use a completely different set of units to talk with you, I'm going to introduce those units to you. And the first unit that we mostly use in astronomy is astronomical unit, or in short term, we call it as AU, right? And this is usually defined the average distance between the Earth and Sun. And usually one astronomical unit is approximately equal to 149.6 million kilometers, or in terms of mile, it will be around 93 million miles, right? And this unit is basically and mostly used to measure the distances within our solar system, right? Uh, and when we need to go beyond our solar system, if those are larger distances, then we need to change the scale and change the units as well. So we are going to use light years beyond our solar system, right? And when you talk about light years, the light year is basically, the idea is the distance that light travels in one particular year, right? Within 1 year, how long a particular distance the light travels, right? And if you convert light year into kilometers, that will be around 9.46 trillion kilometers. So that's a huge distance. You can see that it doesn't make sense to use kilometers and meters in these scales, right? So those are large distances, right? And basically light years we use measuring the distances to nearby stars within our galaxies, right? Basically within our Milky Way, we use most of the time light years, but the astronomy and cosmology is not all about, measuring distances within our galaxies. The technology, because of the development of technology and everything, we are mostly now, look at the objects outside our galaxy and galaxy clusters. And these are actually measured a completely new unit called parsecs, right? Now, parsecs has a different definition, the distance which one astronomical unit subtends at an angle of 1 arcsecond. And the idea that you need to get is the amount of distance included in the 1 parsecs. And if you convert 1 parsecs, it's around 3.26 light years. So that means the parsecs is roughly a little bit more than 3 times of the light years. And if you convert into kilometers, that will be 30.9 trillion kilometers, right? Now you can see that basically the parsecs is mostly used to measure the distances outside our solar system and outside our galaxy. And we use actually inside our galaxy as well when you go for the edge of the galaxies. And now having all these units in your mind, I'm going to show you a small video clip just to show you the size of the universe. And when you look at the size of the universe, you will understand what kind of distances that we are trying to measure. And it will be really fascinating to see, to learn actually the methods that we are going to use, method that we are going to use to measure these distances in different scales I would say, in the most simple way that you can understand, right? So that is my primary aim with today's lecture. And let me just walk you through with this small video clip. I guess this may not have shared yet, so let me share it with you. Right. So this is, I assume that all of you can see my video that is shared in your screen. If not,
Yes, sir, we can see, but the video didn't start.
Right, okay. So let me. Right. I guess now you can see it playing, right? Is it?
No, no, sir,
Not
it's
it?
not played.
No. So let me.
Yes, now it's okay.
It's okay, right? So let me. Now, for some reason, when I make it to the full screen, doesn't play. Maybe the frame rate. So let me check. Right. So for some reason, it doesn't. I think now you cannot. Doesn't play now, right? Can you see it?
Yes, sir, it's not played.
All right. Okay. So the reason is maybe for some reason when uh, so let me I just need to give you this concept only. So let me play it in this way. Now you can see it now, right? Without the full screen.
Yeah, yes, sir.
Okay, so let me play it now. So what I need to show is this is actually a real 360-degree uh, video created by American Museum of National History about the scale of the universe with real data. And let me share the link with all of you if anybody needs to go. And I mean, this is a common, video in the YouTube. You can directly go there and look at it. So for my purpose, let me just directly uh, show what does that mean. So what I am going to show you here is I'm going to start from the Himalayan mountains, and I'm going to uh, zoom out step by step to different scales of the universe so that you will understand this vastness of the universe, how huge it is, and what is the scale that we are talking. And the advantage is once you understand it, it will be much easier for you to understand these different methods for measuring distances and why we are actually using those distances, right? So now starting from actually this is Himalayan mountain range. All of you know about that. Once you know the zoom out it. Let me. Now this is actually planet Earth, the complete Earth. If you zoom it out, and if you go a little bit more distances, all the different orbits that you see here are actually artificial satellites that we have sent out to the space for different purposes. So they are artificial satellites. So if you zoom out a little bit more, the orbits that you see now here are actually the orbits of the planets, right? So different orbits of the planets. And oh, and all of you know about these things, right? So this is our inside our solar system. Uh, so when you get out to the next scale, you will see our sun is right at the center. And now you have this asteroid belt. You know, the asteroid belt is basically between the mass and so these two between two different planets beyond the mass, and basically between Mars and Jupiter. And this is that asteroid belt that you can see. And when you go into this, I mean, this much of a scale, this is roughly, when you go a little bit beyond the asteroid belt, this is actually that if you think about the distance that we are looking at, uh, this distance is roughly 1 hour of light travel, right? So that means if you travel at the speed of light, it will take around 1 hour to reach up to this distance, right? That is the idea. And if you go, if you zoom out a little bit more, you can see that now when you go for the next scale, this is our solar system with all the planets, if you want to look at it that way. So this is around, light travel time is around 1 day. So that, once again, what that means is, if you travel at the speed of the light, you will be able to reach most of the planets within 1 day, right? And even actually, even within 1 day, you can go even beyond that. And now what you can see here is all the constellations that you usually see up in the sky. Now, for example, if you go outside and look at the sky today, you will see a large number of constellations, right? So those constellation patterns are here. They are outside our solar system. And when you look at, just go outside and look at the sky, when you look at these constellations, you need to think about the distance that you are looking at, right? So the distance is the scale of the distance. Basically, when you look at these constellations and everything, these are actually now when you go to this scale, constellations and everything, the light travel time is basically roughly like 1 year, right? So it still take 1 year to travel to these constellations, and I mean around the vicinity of the constellations and around that area. It still take 1 year, even though if you uh, go at a speed of light, right? And so now you can see what happened to our sun. Sun and the solar system is right here at the center. So when you look at the sun and our solar system, is just one solar system out of all the planets and everything that we have discovered now in the universe. It doesn't have a specific place. You can see when you go for this large scale, our solar system is like negligible, right? Now you will see in the next page, all these, the circle dots are actually confirmed exoplanets from our new research. So there are a large number of exoplanets in different solar systems, and all of them are actually, by the way, in our Milky Way. And when you look at this scale, this is around 80 light years. So that means even if you travel at a speed of light, it will still take 80 years to reach out to these positions in the universe, right? And if you go to the next level, you will see how the structure of our Milky Way. So let me a little bit fast forward this one. Now this is our Milky Way, right? So we are just only one particular location. So when you go to the scale of the Milky Way, the light travel time is around 100,000 years. Now you can see even the light years become a large number when you go to the scale of the Milky Way, right? So when you try to measure the distances towards the edge of the Milky Way, it's around 100,000 light years, right? And now we are going to nearby galaxies, right? So the nearby galaxies means, so we have Andromeda galaxy, and we have, small satellite galaxies like the Large Magellanic Cloud, Small Magellanic Cloud. All of these galaxies, they are our nearby galaxies, so they are our neighbors. But still, these neighboring galaxies, it will take around 1 million light years for us to travel. And that probably gives you an idea that they are, from the current understanding about our physics, there is no way that we can travel to these galaxies and try to measure the distances, right? So that's not going to happen according to our understanding right now with basic physics and everything, because it will take 1 million years, even we travel at a speed of light, right? Now in the next step, uh, you can see now, even when we pass our neighboring galaxies, then these are all the mapped galaxies in the universe we have from the data. And you can see this is around 100 million scale. So you have all the galaxies. Now you have galaxy clusters, super clusters, those kind of stuff, right? Now this is the mapped universe, and the empty regions that you have here is actually the things that we still need to map, right? So this is roughly the scale of like billions of years distance, right? Right. You can actually, if you want, actually, you can go back and play it into the backward as well. So I'm not going to do that. So this is all I need to show you. These quasars are one of the most distant objects. And then you can see the cosmic, what we call it as the cosmic microwave background. And this is roughly the size of the universe, which is 13.7 billion years. Now, let me stop the video from here. If you need to look at it, this is a very interesting one to look at. You can actually go back and use from the YouTube, you can look at it. And this is a 360 video, by the way. You can rotate it and look at the other sides to see how it looks like. You can say there are certain parts that are empty, which means actually we do not have data on those areas in the universe yet. And let me stop share and go back to my presentation. So all I need from that presentation is just to give you an idea about the size of the universe, right? So let me stop share this one and go back to my presentation, right? Right, so I hope you can see my screen now. I think you should understand now the vastness of the universe and what kind of distances that you have to measure. And at the same time, you will be surprised to know that I'm going to show you how you can measure distances up to these billions of light years away objects that I just show you in that video. The catch here is you cannot use the same method to measure different distances because of certain barriers, which I will explain, right? Now, by the end of this presentation, you will get a good idea about, at least a basic idea how you can, use these different methods at different scales to measure the distances and why we cannot use one method or the other method. So we call this as a cosmic distance ladder that we will go step by step to right. So I have a question from you asking what is an arc second. So you will get an answer for that in a second, right? So when I go through these different steps, I will explain what arc second means. You all know what arc second is. It's just a word. Right, so let me first explain the most simple way of measuring distances. That is the measuring distances to planets, right? You can see the planets are not so far away, so they are very close to us compared to these other cosmic distances, right? So for something like measuring the distances to nearby planets, we use something called radar imaging. And what we actually basically do is we use a radar, and you send a wave from Earth towards, let's say, for Mars. And this graphic that I showed here in the right-hand side is assuming that it's planet Mars, and you send the radar signal, and it will reflect back to you again as well. Now, if we can find the total trip time, so that means how long will it take to raise to the surface of the Mars and come back for that particular radar signal. Uh, for, uh, for Mars, actually, it's roughly 1,000 seconds. So that means what? And you know the speed of the radar, right? So the speed of the radar is an electromagnetic spectrum. So it should be the speed of light. So the radar will basically move to speed of light and will hit the Mars surface and will come back to you. So you can measure the speed, you know the speed, and you can measure the time it takes for that particular radar to hit the Mars surface and come back to you, if I tell it in the most simple way, right? And from basic physics, you know that if you know the speed and if you know the time it takes uh, for a particular signal to go to a certain point and come back, you can just basically find the distance by speed divided by the time, right? So that is the most simple way of calculating it. And if you do it in that way, this is the answer that you will get for the distance to the Mars in terms of kilometers, right? Now, this is the most, the most simple way of measuring distances to these nearby galaxies. But when you go for the faraway objects, let me see you this one right here. When you go for example, you don't need to go for very huge distances. Let's say you go for you need to measure the distance to the nearest star, right? So what is the nearest star for us? Anybody knows the answer? What is the closest star for us? Anybody would like to comment on that? So that will be actually, I mean, you can actually use the chat window if you would like to answer, and I would highly appreciate it. Yes, Priyankan, thank you. And that will be Alpha, uh, uh, Alpha Centauri. And I have another answer called Moon. Uh, it is correct that Moon is the closest object for us, but Moon is not a star, by the way, right? So the stars has a different definition and different way of right. So I have another answer. The closest star is Sun. That is exactly correct, right? The Sun is actually the closest star for us, right? We have the Sun at the center, very close us. That is, in fact, the correct answer, right? So if you skip our Sun, which is in our solar system, if Sun is not considered, what will be the closest star for us? For us, answer for that is actually Proxima Centauri. The Alpha Centauri is also very close by, but the closest one is Proxima Centauri. I would say both are very close to us, right? Now this Proxima Centauri is around 4.24 light years away from us. Now, if we try to send a radar signal for this one, and try to measure the distance, what will happen? How long that we have to, wait to measure the distance? Because it will take 4.24 light years for that. I mean, we now know the distance, right? But it will take around a little bit more than 4 years to reach to the surface of the Proxima Centauri and another 4 years to come back, right? So roughly close to 10 years it will take to measure the distance. Now you can see that this is not practical, right? Now, this is why you cannot use radar signals, but this is not the only reason, by the way. This is just one reason. There are a lot of other reasons that it is not practical to use these signals because of the different losses and, the signals get weak. There are a lot of other reasons which I'm not going to discuss here basically, but the basic idea, you can see that it's from the knowledge that we already have, it is not practical to use uh, these radar signals to measure the distances to these, even for the nearby stars. So we have to go for another method. So let's see how we can measure the distances to these nearby stars. And in fact, the answer seems to be very simple than you think. So we use something called parallax measurements in astronomy. Now, if you know a little bit of trigonometry, this is very simple to understand. Yet very powerful in astronomy. And what we do is, you can see here from the diagram right here, I think all of you know about the parallax angles, right? So you use this, you can measure, let's say this is the star that we want to measure the parallax angle. And this is the sun, this is our Earth right here. So if when Earth is in this side and when Earth is in that side after 6 months, it creates this angle right here, which is in fact the parallax angle that we called. And all you need to do is, we know the distance from Earth to sun, and what we actually need to measure is the distance to the star from Earth, basically this distance, right? Now, if we can measure this angle, which we called as the parallax, you can easily calculate the distance, right? So that's very simple. The equation that we use in astronomy to measure the parallax angles is actually this equation right here in the top right hand corner in your screen. I have not mentioned here how you can derive this, and this is very simple trigonometry. If you just go and search in the internet, you can find it. So assuming that this is a small angle, you can just take the sine theta values and easily derive it. So once you go through that small derivation using trigonometry and substitute proper units, right? So that is the only important thing when I substitute proper units. And you can see that you have arc seconds here in the equation. You get this equation right here, right? The only thing is, when you measure this angle right here, which we called as the parallax angle, and that angle has to be substitute in arc seconds, right, for the equation. So let me just, since you have asked, let me just introduce you what this arc second means. And I assume that all of you know what a degree is. When you measure the angles, right, in mathematics, you use degrees, and usually we assume that we have 360 degrees if you rotate one complete circle, right? So that I guess you can understand. And for each degree, you subdivide a degree into 60 equal parts, and one small part from this 1 degree, I mean, from these 60 divisions, we call it as an arc minute, right? And when you divide this arc minute further into smaller sections, uh, I mean, you take the 1 arc minute and divide into 60 divisions. And one of those divisions is what we called as arc seconds. And you can see that it's just a smaller measurement than degree, right? And still a measurement that you use to measuring angles. The reason that we use arc second here in astronomy mostly is because the parallax angles that we are measuring is very, very small, right? So I hope this will answer your question that one of you had, what arc second means, right? And let me go back to the previous slide, right? So what you are going to do is you measure this angle right here, and you can measure it, right? In astronomy, that's all what we are doing. We use instrument to measure this angle. And once you measure the angle, you convert it into a distance from this simple equation. And you can see that this is a very simple way of measuring the distances, right? And if you take our nearest star, which is Proxima Centauri, you can, in astronomy, you can go and measure these parallax angles. That is doable. And if you measure the parallax angle, the angle came out to be 0.7687 arc seconds. Now you can straight away see why I am using arc seconds in terms of degrees, because if you are going to use degrees here, this will be very, very tiny number, right? Because these angles are very small. And you just take 1 over 0.7867, which is the parallax angle, 1 over P. Then your answer will be 1.30 parsecs, right? So don't worry about actually how these units here comes and everything here, because this is not a very hard thing to, prove. Even if you go and search in the internet, you can easily find from a small trigonometry how you can do it, right? So my purpose here is just to show you how you can do these things, right? Now, At the same time, you should understand that what happens when you go a little bit far away. What happened to this angle, parallax angle, when you are trying to, measure the distances that are so far away. If the star is so far away, what happened to this parallax angle? It will become smaller, or yes, exactly correct. Priyankan, the angle will get smaller and smaller, right? Now, this is exactly one of the problems we have when we, measure the distances, even using the meter ruler and something, right? If you need to, measure something very small, the meter ruler sometimes doesn't work, right? Because that smaller values, because the minimum that you can, measure is usually 1 millimeter, and if it is smaller than that, you cannot use it, right? So the same thing happens in astronomy. And so what happens is there are some limitations to measure the distances using arc seconds, measure using parallax angles, because if the object is very close or the star is very close, that's okay. You can measure the parallax angles. Even the closest star, you can see that the parallax angle is 0.7 something, right? So that also indicates you when you go for very large distances, what happens? These parallax angles become smaller and smaller and smaller, then it will come to a point that you cannot even measure it, right? So that is the problem with this method. So you can use it, but for a certain limit, right? And let's see in astronomy whether we are using it, right? So that's also important. Now, specifically measure these parallax angle measurements, we are using now modern technology. And we have one of the two most famous spacecrafts sent specifically to measure the parallax angles. And in 1990s, if I remember it correct, there was a satellite called Hipparcos satellite, which is sent out to space to measure specifically these parallax angles for stars and then calculate the distances, right? And it basically used this method that we described. And you can see that the starting basic idea is very simple, but still they use this idea to measure the parallax angle. And this particular satellite called Hipparcos has actually measured around 100,000 stars, parallax angles to 100,000 nearby stars. But they had a problem with not the problem, actually, this instrument has a precision of 0.002 arc second. So that means if the parallax angle gets smaller than that, this particular instrument cannot measure it. So this is like we are using meter ruler, but if there is something smaller than 1 millimeter, it is hard to measure it from a meter ruler, right? The same concept apply here. And that was the technology we had at that time. And therefore, we could only measure distances up to 500 parsecs at this time. And beyond that, we cannot measure, right? But 500 parsecs means still a very large distance, if you remember the distance conversion, right? Now, in 2012 or 13, we had another satellite with very modern technology called Gaia. And this satellite actually could measure the parallax angles as small as 0.00001 arc second. And you can see how the technology has developed. But the important thing here is you can still use the same concept, right? The concept doesn't change, but the technology changes. So what you are doing is apply the same concept to this latest technology. And this particular uh, uh, the telescope or the spacecraft is very, very powerful. And up as far as I remember, until 2000, it has been still, it's still going on. The mission is still going on. And as far as I remember, it kind of measured up to 1.4 billion stars, the parallax measurements, right? And if you take 1.1 over 1.00001, you can get the idea that what kind of distance that it can measure, right? So it's a huge distance. And you can see the number of stars that we have measured the distances now. And if you like to look at these distances, there is a database. It's you can actually uh, 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 measure the distances so that you can actually get the data and look at the distances if you like, right? And even there are students who do research using these. You just get the data and look at, I mean, you analyze the data and get, I mean, you can uh, measure the distances. Madhushan, I have a question here asking whether the guy has BH1, BH2, something like that. Are they measured by using this? I'm not sure about these notations that you have mentioned. I know that there are several mirrors inside this for this the technology to work. I don't know whether you are referring to that, but basically the measurement unit will be still uh, basically, when you look at the database, they usually measure things in terms of milliarc seconds, not arc seconds, but still you can actually convert it, right? Right. Now you can see that measuring distances, this still takes, you can go a certain amount and you have to stop, right? So even you consider about the Gaia satellite, the measurements that we are taking is still inside our Milky Way and for nearby galaxies. And there are certain times that we have make measurements of the stars using Gaia in nearby galaxies as well. Uh, but there is a limit for that, right? So now we have to think how we can measure the distances when we are going beyond the Milky Way, right? So this technology has a limit. You can see that uh, up to this much, after up to this much of accuracy, you cannot, use this method because this parallax angles getting smaller and smaller so that you can look at the stars, right? Now, even when you even go for these distance galaxies, you cannot even see stars separate, right? So there is no way the technology is not developed up to a point that you can resolve the stars when you go for these distance galaxies, right? Right. Now, keeping that in mind, let's see what is the other method that we can use to measure the distances when you go beyond our galaxy, right? And sometimes in our galaxy as well, when you go close to the edge of the galaxies. Let me now, before I go into this next method, I want to introduce you a brief, give you a brief idea about this brightness of stars, because when we talk about the next method, we need to consider the brightness of the star, because the brightness and the distance are kind of, there are equations that relate those two, which we are going to use for the measurements in the next method. Now, uh, you all measure the brightness in day-to-day life, right? So if you just look at the light bulb, you can tell how bright it is. And what you know is that depending on the number of watts that you have, also depending on different bulbs, you will see even different brightness amounts, right? So you can see this one is brighter than the other one, this bulb is brighter than the other one. Now this brightness can vary into different reasons, right? So one reason could be they are at different distances. Even if you have a similar kind of bulbs in two different distances, the bulb that is close to you will be more brighter, right? And there could be other reasons, maybe another bulb, even they have at the same distance, if the intrinsic brightness or the amount of watt maybe is lesser for a certain light bulb, then one bulb is brighter than the other, right? Or one bulb is dimmer than the other. Now the similar situation applies for astronomy as well. And there was this astronomer called Hipparchus, and his name was actually used for that satellite as well. He actually was the first one to measure the brightness of stars. Basically, look at the sky and just record how bright a particular star is. That's what he did, right? I mean, he actually went on extra steps further and cataloged or recorded the brightness of around 1,000 stars, and he found that when you look at the brightness, he can categorize these 1,000 stars into 6 categories. And what he did was actually he sorted these brightness levels and then categorized those into 6 categories and gave a number based on the brightness, right? Now, what he did was he gave uh, the largest number to the faintest star. So the brightest category, he gave a number 1, and the next brightest one number 2. Like that, when you go for the faintest end, he gave the number 6, right? And later, the astronomers developed this little bit more, and then they understood that when you look at these brightness values and the magnitudes that we have for these different brightness stars, the difference of 5 magnitudes that he had, because I told you that he gave number 1 for the brightest stars and number 6 for the brightest star. So the difference is like 5, right? So that difference is account for brightness ratio of 100. So that means if you take number 1 star and a number 6 star, number 1 star is basically 100 times brighter compared to the number 6 star, right? So that's how his scale works. Basically, he developed a scale to represent the brightness. And now in astronomy, we call this as a magnitude scale. And we use this scale to measure the brightness of stars, right? And this is a very a summarized way of understanding this magnitude scale that we have for the stars. And all of you know about our sun, which is very bright. Even you cannot, look at the sun from naked eye at the daytime, and even don't do it actually. And uh, the brightness of the sun is around minus 26, right? So, and if you take the full moon, it's easy to see up in the sky when it is there. It's very bright, and it's around minus 12 or 13, right? And if you think about these, the bright planets that you can see from your naked eye, Venus is around minus 4, around minus 4, and Jupiter and Mars is around minus 3. And you have these, I don't know whether if you have looked at the sky, you can see these star Sirius, Alpha Centauri, and Betelgeuse, Polaris. These stars you can see up in the sky. Polaris is probably a bit harder to look at from the sky from Sri Lanka because it's very, very close to the horizon. And there is a limit that you can see faintest object visible to unaided eye. So that means any object that has a magnitude larger than this, it will be harder for you to see from your naked eye, and you need a telescope, right? So that is the idea, right? And so this is how you categorize the brightness of, how you place different stars depending on their brightness into this magnitude scale. And something that is interesting for you to understand here is if a star is brighter, it has a lower value, right? If a star is fainter, it has a higher value. That came from the definition made by Hipparchus at the first point. So as a convention, it continues, right? So it is important to remember that the magnitude scale is actually works in the reverse order. And there is a relation, these magnitudes that we actually measure is we usually called as apparent magnitudes. The reason is that we don't know the distances to the stars. We just look at the sky and just record the magnitudes or the brightness values, right? Now, that is actually not a fair way of comparing things, right? Because the different brightnesses are, maybe actually they are brighter, or maybe because they are at different distances. For example, even though if you have a very large, very bright star, if it is so far away from us, then this particular star may be uh, fainter for us because it's so far away, right? Not because it is not brighter, right? Now, same thing applies for our sun. Our sun is very bright for us, Actually, if you that's because basically the sun is very close to us, right? Not because the sun has a very specific brightness in the universe, right? Sun is a very ordinary star as the other stars. Sun is just brighter for us because it's very close to us, right? Now, because of that, astronomers wanted to compare these different brightness values in the same scale, right? To make it fair. So they introduced something called absolute magnitude for that. What they do for the absolute magnitude is they bring all the stars into the same distance. And as it is defined, basically we call that as a 10 parsecs of distance. You keep all the stars at a distance of 10 parsecs and look at the brightness and give a magnitude value. And this is called absolute magnitude, right? And that is usually defined from this capital M. And there is a relation between the absolute magnitude and the apparent magnitude, which is given from this particular equation, right? I'm not going to show you how it comes or something like that. This is actually not very difficult thing to show up, but my aim is just to introduce you this equation to go into our next step about different way of measuring distances. Now this is absolute magnitude and this is apparent magnitude, and this d is the distance, right? Now you can see that this absolute and apparent magnitude of stars are related with the distance, right? So this also indicates you if you can measure the brightness and convert those into the magnitude values, we can actually get an idea about the distance, right? So that's all we need for this particular section. And let me go for the next section. How do you measure the distances beyond the Milky Way, right? Now we can use parallax methods up to certain point, but anything beyond the Milky Way, we cannot use that, and we know the reason, and we need to find a different method, right? And that's exactly what we are going to do. And now there is an interesting story behind, measuring distances beyond the Milky Way, because this all started with this a debate called Shapley and Kurtz. And this debate is all about actually at 1910s, like early 19th. This is around like more than 100 years ago for you. They actually detected an object called nebula, because nobody knows about galaxies beyond our Milky Way at that time. But they have a problem with this. The problem is that whether this spiral shaped nebula, and this is actually Andromeda galaxy now, by the way. So let's say Andromeda galaxy, but they didn't know about, nobody knew about galaxies outside the Milky Way at that time. And what they need to know is whether this particular nebula or the galaxy, whether this is inside the Milky Way or outside the Milky Way, right? Now how to, and there was a debate about this. There was an astronomer called Harold Shapley. He believed that this Andromeda galaxy, or the nebula as they called at that time, is a part of our galaxy, not outside it, right? But Kurtz argued that it is not the case. This should be beyond our galaxy, right? Now the problem is how to solve this issue, right? Now this is a real scientific problem that they had, and they need to come up with the answer. And what is the solution? And they actually need to find the distance for this one, right? Because even for your day-to-day life, if you need to know whether a certain thing belongs to, let's say, you have a certain town that you need to think about whether it belongs to this district or the other district, you are measuring the distances, right? So that's exactly what we are doing here. But they didn't have any idea about the distances at that time, and especially how to measure the distances beyond the Milky Way, right? So they need to find a new method for that to basically to solve this debate and find out whether this particular galaxy is in our Milky Way or beyond our Milky Way, right? Right. Now, to do this, they found a new method, and there was uh, a woman astronomer called Henrietta at that time, and she was actually doing some research about different thing, which we call Cepheid variable stars. And if you don't know about, there is a certain category of stars that we called as variable stars in astronomy. The name comes because they change their brightness with the time because of some internal things that goes on. They change their brightness with the time, and these are actually called Cepheid variable stars. Uh, those variable stars, they have different kinds of stars, right? So they give different names based on the nature that they behave, this variability of the stars or the change in brightness. And when it comes to Cepheid variable stars, it's a different category. And these Cepheid variable stars, this particular astronomer, Henrietta, she actually, in 1908, she found there was a very specific feature about these Cepheid variable stars, right? And she was, using the telescope and observing these Cepheid variable stars from her telescope. And she was measuring the luminosity of these stars and estimated the distance to these galaxies, right? And what she actually noticed is that these stars actually change their brightness very regularly, and they have a period, right? And to make it clear, if you look at this graph right here on the top right-hand corner, these Cepheid stars, they change their brightness in this pattern. So they increase, decrease, increase, decrease like that, right? And this change has a period. So that means for every, let's say 10 days, they increase the brightness and decrease. And for the next 10 days, it does the same thing like that. There is a period for these changes, right? Now, what she did was she actually observed large number of these Cepheid variable stars and look at their luminosity, right? The luminosity is again the intrinsic, let's say it's kind of an intrinsic brightness of a star, which is related to the absolute magnitude. So let's put it in that way. And when she actually made the observations for the periods and the luminosity of this large number of stars and plotted it, this is what she got, right? It seems like when the period increases of a particular Cepheid variable star, the average luminosity or the intrinsic brightness or the absolute magnitude also increase. And the interesting thing is the relationship is actually a linear relationship, right? So this is like the mostly y equal mx type relationship, right? So very close to this linear relationship. So she made this graph, right? So what is the use of this one? Now, once you have this graph, if you can find a Cepheid variable star in a distant galaxy, and if you can find the period of that, you can look at this graph and look at, let's say, if the period is 20 centimeters, okay, then its absolute luminosity is this much, and you can relate the absolute luminosity to the absolute magnitude very easily. It is very straightforward. And so you know the absolute magnitude of that particular star, right? And if you can directly look at the star, the visual brightness can be measured and converted into the apparent brightness, right? So when you know those two, you can actually measure the distance. Now, once this period luminosity relationship is well established, and this is actually very famous in astronomy, what happens is this is the method that you can find, and you observe as you see in the diagram A, you observe the Cepheid variable star and try to measure its period, uh, how long it takes to, vary its brightness and come back to the initial position. And then you use that period luminosity relationship to calculate the star's luminosity, and that will give you the absolute magnitude. And then you measure the star's apparent brightness. That is, you just look at the star and measure the brightness that will be apparent. You can convert that brightness into magnitude from that magnitude scale, right? And once you know the apparent brightness and the absolute apparent and the absolute magnitude values, you can use this equation that I just introduced in the previous slide to get an idea about the distance. So that's how it works. Now remember this debate that they have, and all of you know about Edwin Hubble. He is very famous in astronomy. And he took this challenge and he went to one of the largest telescopes at that time. This was in Mount Wilson in Southern California. And he actually uh, observed Cepheid stars or Cepheid variable stars in this Andromeda nebula of the galaxy and measured the period. So if you can do that, then you know the period. You go to the period luminosity relationship and find the absolute magnitude and find the apparent magnitude. You can measure the distance, right? So that's it. So job done. And what happens is when he measured the things in this way, he found that this Andromeda galaxy is about 1 million light years away from us. And this is clearly beyond the size of our Milky Way, right? And this established the first confirmed evidence that Andromeda is our nearest and still a separate galaxy, right? So that's how this particular method established at that time to measure the distances. Now, this is the first method that we are going to use to measure the distances outside our galaxy, right? So still, even now, if you can go outside and try to observe a period of one of these Cepheid variable stars, you can find the distance to that galaxy using this method, right? And this is called period luminosity relationship, right? Now, what is the problem with this method? Now, if you want to use this method, you have to observe the stars in other galaxies, right? Is it doable? That is the question. Yes, it is for nearby galaxies, but the problem is when you go for these galaxies that are so far away, let's say 100 million light years or 1,000 million light years, then you cannot actually see these individual stars inside galaxies, right? Now, for example, I don't have time, but I can show you if need in a separate day. I have observed these large galaxy clusters using this very large 4-meter telescope. And what you can actually see is uh, the galaxies in these galaxy clusters. Inside galaxies, you cannot actually observe the stars because the telescope is not capable of resolving and look at the stars when you go for like 200 or 400 million light years away. Or I think the galaxies I observed is around 400 to 2000 million light years away from us. So you cannot actually resolve those stars inside that. And I mean, if you cannot look at the stars, then how you can use this method? Because you have to locate the stars and measure the period for that, right? So that's not going to work for the stars that are for the galaxies that are very large distances away from us, like 100 millions, 200 millions, 400 billion light years away. You cannot use this method. Now you have to go for a different method, right? So that uh, will take us to the next step in our cosmic ladder to find the distances, right? Now, this is called measuring distances using type 1a supernova. Now, the problem is now, then you need to know what is a type 1a supernova. Anybody knows what supernova, what supernova means? You probably have heard that the supernova means explosion of a star, right? So there are different types of supernovas. Now, to understand the supernova, you need to, study and try to understand the whole stellar life cycle that we used to have, right? So usually there is something called molecular clouds in the inside, galaxies and everywhere. And there, once a certain condition is met, these molecular clouds become a protostar, and this protostar, when we classify, meet certain criterias, there are a lot of physics and things going into that. I'm I will go through very briefly just to come to the point about the supernova. What happens is these low mass stars, there are stars that has very high mass stars, certain stars has very low mass. So they go through some nuclear fusion reactions at the center and become something called white dwarf stars, if you heard about it. And these white dwarf stars, they are very tiny, and they have carbon at the center of these white dwarf stars. When they have another star nearby, we call as a binary star nearby, this, because of the gravity that you have from the white dwarf stars, these white dwarf stars actually accrete matter uh, from this nearby star. And once it has a lot of matter accreted, and if the mass of the star exceeds a certain limit called Chandrasekhara limit, this whole star explodes, right? And that's what we called as a type 1a supernova. Actually, you don't need to uh, know about everything, but if you look at this diagram in the left-hand side, this is exactly what happens during a type 1a supernova explosion, right? So if I play it again, what happens is right here you have a white dwarf star, and there is a nearby another star that from that star, this white dwarf accretes matter due to the gravity. When certain amount of matter accretes, like that you see in the image here, the brightness increased unusually, and even for a galaxy that is so far away, let's say 100 million light years away, if you have to have a type 1a supernova explosion, because of this huge brightness, the whole galaxy will outshine by this particular star. And at that point, you can take any measurements of this star, right? And that's how it works. And this is, in fact, why this type 1 supernova is very important to measure the distances in very large distances, because when a supernova happens in a very supernova explosion happens at a very large distances, even millions of light years away, even though you cannot resolve the stars inside that, when supernova explosion happens, the brightness increases dramatically, that the whole brightness that you have from all the stars and everything in the galaxy is still smaller compared to the brightness of this galaxy. Because of that, you can easily detect the supernova in that galaxy, right? So that is the basic idea that you need to know. And there is another interesting thing about the supernovas. And I'm going to play this video, and what you can see here is in the left-hand side, you can see what happens during a type 1 supernova, how the brightness increases and everything. And the right-hand side, there is a graph with over the time, it will plot what happened to the brightness of the supernova explosion, right? And so this is actually what happens with the over the time. You can see at this particular location, there is a supernova explosion. And what I am recording here is the magnitude of that supernova, right? Brightness, what happened to the brightness converted into the magnitude, right? And you can see that the brightness increases and up to a maximum point, and then it will decrease after some time, right? So that's what happens during a type 1a supernova explosion, right? In that way, right? So that's what happens. And this top peak right here is very important for us, because that is the main characteristic, or the main uh, property that we need to measure the distances, right? And the interesting thing about these type 1a supernovas is, regardless of where it happens at what distance, uh, this peak luminosity or the peak brightness is the same. It doesn't change. So that's a kind of a property unique for type 1a supernova. And remember that I'm not going to teach you about the supernovas today. And there are other type of supernova explosions which are not useful to measuring distances, right? So we are only concerned about this type 1a supernova. And this peak brightness or the peak absolute magnitude will not change regardless of where it happens, in which galaxy cluster, which galaxy it happens. That value of m will not change, right? So that is roughly around like minus 19.3. That is a very specific property for these type 1a supernova explosions, right? Now what happens is, if you, and now this will give you the answer how we can measure the distances using type 1a supernova explosion. So you are carefully looking at all these galaxies that are millions of light years away. In case there is a type 1a supernova explosion, you are trying to get this curve. And if we have a type 1a supernova explosion, we know the peak brightness and can convert it into an absolute magnitude. And then when it is very bright, you can actually measure the apparent brightness very easily, right? Because it is very bright. So you measure the apparent brightness. Once again, you know this apparent and absolute brightness, and you can measure the distance, right? And that's how this method works, right? In more simple way. By the way, if there is someone who knows, a little bit more about the astronomy, you will understand, you will know that there are a lot of, modeling and parts going into this when you do it in the actual way, but this is the basic idea how to measure the distance, right? Now, the advantage is actually the type 1 supernovas are actually very, very useful, because you can actually use this type 1a supernova explosions to measure the distances up to 1000 megaparsecs if you want, right? So that's a huge distance, right? So you can, measure the distances of galaxies up to billions of light years away using this method, right? That is the other method. But there is a limit for this one as well, but you can measure the most of the distances. But there are other issues when you go for so far away, like 10 11 billion years away. Then there are issues with, there are cosmic dust involved with that. You don't get the brightness because of these, the light become weaker when it reaches to us. There are other kind of practical issues when you go for very large distances. But up to 10,000 megaparsec, this will be really good. And beyond that, the reliability kind of a little bit decreases. And this is the point where we need to go for the last method that I am going to discuss with you about measuring distances, right? Right. Now, I guess this last method we called as the Hubble's law for distance measurement. And let me oh, it's already 9. How long we can continue actually?
So we can continue until 8.
Right. So
It's
that means,
okay.
I mean, maybe around another half an hour, right? Is it?
Yes.
Okay. Right. It will not take that much. So there are only few slides here. So I don't want to, go for like too long. And there are other questions that I can see in the chat. Maybe I will take some of those at the end. So the idea is actually, let me go back. Right. Now, when we after we know this distance measurement using supernova explosion, there is another method came out to measure the distances, and this is using Hubble's law, and this is specifically used only for these extragalactic distances. And what we actually use here is something called redshift, right? Now, redshift means, if you know that if you have done some A-level physics, or even if you haven't done anything, just you know that for the sound, If you take a horn from a bus or something like that, when it comes towards you, the sound increases, and when it goes away from you, sound decreases to you, right? So you don't hear the same sound. But the horn has the same sound, but when you hear it, it depends on the relative motion between you and that particular source, right? And uh, when you go for the light, that also applied. When there is something comes towards to you, uh, the observed light will increase, the wavelength will increase, and if something moves away from you, the wavelength of the light will be decreased. And we usually used to use the term called blue shift and red shift for this one. That's because the red means the larger wavelength, blue means the smaller wavelength. If something comes towards us, we used to tell that it is blue shifted, right? Because the wavelength decreases, and if something goes away from us, it is red shifted, right? And that is called uh, red shifted. And this is, some of you have suggested the name. This is actually called the Doppler effect, usually, right? And in astronomy, what mostly happens is what we know is that our universe is expanding itself. So that means the space itself is expanding. Since all these galaxies and everything are sitting on the space, they are actually moving away from us with the space. So that means these galaxies are mostly redshifted. There are some exceptions like Andromeda, which is slightly blue shifted, but I'm talking about in general, almost all the galaxies are usually redshifted. And there is a relation, you can actually measure this redshift, right? And this is exactly what this astronomer called Vesto Silper did in around 1912. What he did was he take some spectra of these galaxies and observed uh, that these galaxies are actually shifted towards the red side. The wavelengths are shifted towards the red side, and that is understandable because these galaxies are moving away from us. And so we define a value called redshift based on that, and this is nothing else but you just take the observed wavelength and then you subtract the rest wavelength. So rest wavelength means if this particular galaxy is stable and does not move, what will be that wavelength, right? It's kind of, we used to tell this as a laboratory wavelength, and you divide it by the rest wavelength, and then you will get a small number for this one without any units. And that particular number is what we called as the redshift value of a galaxy or a galaxy cluster, mostly for galaxies. And once you know the redshift value, if you multiply the redshift value from the velocity of light, uh, this will give you how fast a particular galaxy is moving away from us. And I have mentioned the equation here, right? And what this astronomer Wester did at that time was he measured these redshift values from some spectrum, and also he knew how to measure at that time they knew how to measure the distances to these nearby galaxies using this period luminosity relationship that we discussed little while ago, right? So he plot these two values. That means how fast a particular galaxy is moving away from us, and the distance to that particular galaxy. And interestingly, this is something what he got uh, when he plot these two values, right? So the x-axis is the distance that he measured from, let's say, period luminosity relationship, because you can actually measure the distances to nearby galaxies from that. And then he used these redshift values to calculate how fast a particular galaxy is moving away from us. And interestingly, what he found is that when a particular galaxy is far away from us, it moves faster away from us, right? So that's what this particular relationship tells you, and it seems like it's a really linear relationship at that time. And he can actually find a constant from the gradient of this graph, which is converted as the Hubble constant later, right? Now, using this information that I just told you, if we initially they found this relationship and found the Hubble constant, and then they realized that Hubble constant is a universal constant. It doesn't change. And when I tell it doesn't change, actually, there are some uncertainties when you go for the larger distances, by the way, which I'm not going to explain here. Let's say the Hubble constant is a constant. Then if you know the redshift, you can find the recessional velocity or the velocity that a particular object is moving from us. And if you know those two values, you can find the distance, right? So that's is actually the next method that we have. For example, this is one of the plots that I made myself for some of the data. And on the x-axis, you have the distances. And by the way, this is from the latest, this is using data that we have right now, not 100 years ago, because 100 years ago, you only knew how to measure the distances to nearby galaxies. But now we know how to measure the distances that are so far away from this type 1a supernova explosions, right? Because of that, I have increases the distance up to 1200 megaparsecs here, and the velocity is up to 70,000 kilometers per second. So this is so far away. And when you take the slope, this will give you the Hubble constant, right? H naught value, right? So this is for what the Hubble is actually famous. Now, if you want to find the distance using this method, what you need to do is you have to find the redshift value of that particular galaxy. And this can be done using few different methods. More simple way is you take the spectrum of a galaxy and see a particular wavelength is how much it is shifted. And then you go to this particular equation right here, this one right here, and calculate the redshift value and multiply it by the velocity of light and find the recessional velocity. And if you know the recessional velocity, I have a sample calculation here. You take the recessional velocity, divide it by that Hubble constant to find the distance, right? And having mentioned that, I need to emphasize you at the same time, as you have see here, is this redshift multiplied by the recessional the velocity of light for the to obtain the recessional velocity will only work for these low redshift galaxies, because when you go for high redshift, it's a different story and different equation, which I have not mentioned here because the things get a little bit complicated after that. But this is the idea that you can actually use it for very large distances as well. And you can see that I have a small graph here just to show you when you measure the redshift distances, what happened to the distance. When you go for larger redshift values, you can see that when the redshift is equal to 10, that will be measuring 12,000 megaparsecs distance, right? That is 39,000 million light years. Like that, you can go for very large distances using this method, right? And so this is very useful when even the type 1a supernova method is not working for these huge distances, or become less reliable for very large distances. When you go for these billions of light years away, we usually use this redshift method to measure the distances, right? Right, so let me, actually you can use that to measure the age of the universe as well. which I'm going to skip here for the time being. But you can understand that uh, from the things that I have discussed up to this point, we are using different methods to measure the different distance scales, right? Because certain methods has limitations, so we need to, go for the next method. And I also want to emphasize you that these are not the only methods that we are going to use to measure distances. Okay? So there are other methods like called Tolley-Fisher relations, and there are intermediate methods that you use something called, star clusters and main sequence methods. There are a number of other methods that you use to measure the distances, but basically this is like a summary of measuring distances. And as the last thing that I just want to show you, one of the more profound findings came as a result of knowing about these measuring distances is this graph right here. And this is again a Hubble plot, and what happens to the velocities and the distances when you go for very large, higher measurements that are so far away, right? So actually what happens is you can see that when you measure, now this plot that you have is number of data points that you have, and you can see that the points are kind of curved towards the end when you go for larger distances, and these measurements are taken independently. If you want to tell it like you measure the amount of redshift and find the distance, right? Sorry, find the recessional velocity, and then you use the type 1 supernova distance measurement to measure the distances to so far away galaxies. And you can see that instead of having a straighter line that I had, so if I go back to this particular graph right here, you can see that I go up to 1200 megaparsecs. It seems like it's a straight line, the Hubble constant. There is no issue with Hubble constant, right? But if you go back to here, I'm using, go up to 4000 to 4500 megaparsecs of distances. And now you can see that uh, you can actually see that those are the small points that I measured previously for the smaller distances. Now, when you get a lot of data points in this region, now it looks like this is curved towards this side, right? So that means what? Can you understand that it seems like it's slowing down, right? So what that actually means is when you go back to larger distances, right? What happens is the recessional velocity kind of slowed down, right? So what that means is, even though now in the past, the universe actually was not expanding as fast as we thought, now it's expanding faster, right? If uh, if you can understand it correctly, right? So that this idea, this means actually the universe is accelerating, right? So we have the idea about this universe is expanding, everything is moving away from us, and we thought that this expansion is going through a constant rate, and that's why we have a kind of a straight line that you have a constant rate. And what I have here is when you go for further distances and look back to the history of us, because when you are looking back larger distances, that means you are basically looking at the history of the universe, right? In history, the recessional velocity, it was actually in the history of the universe, the things are not moving faster as how it looks like now. So what that means is earlier it was slow, now it's faster, which means universe is actually accelerating now. Now this became now this is one of the huge discoveries that we have actually in 2011. The people who got this discovery got the Nobel Prize as well, and uh, that's actually one of the major discoveries that we have, and astronomers name this particular component that may be leading to this accelerated expansion of the universe, maybe the dark energy, right? And dark energy does not mean that it is dark and there is an energy, so it's just a name, right? And because the idea is everything is usually, attracted towards each other by gravity. When the universe expands, the gravity get weakens, and what they expect is this will be either constant or maybe slow down, right? But now when things get take up and get accelerating, so there should be something, a kind of force that works like an anti-gravity thing, right? Just opposite to the gravity. So that's what happens. So what I know, I don't want to talk about the dark energy a lot here. What I want to tell you is that this method about measuring distances using type 1a supernova distances, it what makes this the discovery of the dark energy at the end, right? But even though we tell that it is a discovery of dark energies, we know that there is something that uh, lead to the accelerated expansion of the universe, which may be dark energy, and but actually for up to now we don't know what it is exactly, right? But this discovery of the expansion of the universe is basically because of due to these findings came from this measuring type 1a supernova using the distances using type 1a supernova, right? So that's what important here, right? So I hope you can understand this. And actually, I just need to give you an idea about, how important is this distance measurement. And with that, with this particular picture that we have about the universe, you can see that this is where we are right now, and we are in an accelerated expanding universe, which is one of the major findings due to the understanding of distance measurements using type 1a supernova, right? And that's what I need to just mention. I mean, you don't need to, go to and understand it, but my take home message is just understand there are how we use these different methods to measure different distances. And more importantly, if you are science students, the scientific thinking behind this, that is actually more important for you, uh, while understanding these concepts, how they think about about different solutions, and when they come up with different problems, they came up with a solution and it is scientific, right? How we thought about it. So that is the most important thing. And just to summarize, what we actually talk is about the different methods of measuring distances, starting from these radar measurements for small planets, and then we nearby planets, and we move on to measuring nearby stars using parallax angles, and then period luminosity relationship to nearby galaxies, and then we use type 1 supernova distances when we need to go from further away. And then for billions of light years away, we use this redshift method at the end using the Hubble constant, right? So that's all we discuss basically. And I'm going to stop from here. If you have any questions, you can ask now. Right? Thank you. Right. So let me see whether I can. There are some questions here asking. Any problem to measure that the distance due to the expanding universe, the supernova for for your question, you are asking, one of you asking the two black holes make a supernova? No, actually, what happens is uh, merge of two black holes is a different story. The making actually the supernova type two supernova occurs before you have a black hole. Actually, there was a when you have a huge mass of the high mass star, it basically go through a process called, you go through different processes and have very heavy metals at the center. And then there is a process called photo disintegration. And after that, you get uh, a neutron core at the center. And because of that core, it goes through a huge blast for the incoming materials, which make a type 2 supernova. And after that step, if the mass is very huge, a particular star may become a black hole. So that's how it happens, not merging two black holes. And you have another question, is there any problem to measure the distance due to expanding the universe? Uh, uh, yes and no, because your question is very valid, because when you go so far away, due to the expansion of the universe, actually the light signal comes from us will shift to different wavelengths. So it will become a different story, and this is why we will have issues to measure. Actually, this is one of the reasons that we have some issues when we measure the distances to the galaxies that are billions of years away from us using supernova. And that's why, in fact, we used to say that Doppler, this redshift method is more reliable when you go for larger distances. And right. So there is another question. Is redshift due to the expanding universe, and why Andromeda galaxy is blue shift? So good question. And so actually the reason is that uh, when we talk about redshift, there are three redshift, right? I would maybe let me talk about two now. One is called Doppler redshift. Now, Doppler redshift happens because of the relative movements of the two objects. Now, uh, the one thing that happens for all these galaxies is because of the gravity, everyone will be attracted to every other one, right? For example, if you take the Andromeda galaxy, it is evident that because of the gravity, those two will be attracted to each other, right? So that means it should come towards you, right? So if something is come towards you, the blue shift is the one that should happen, and that is because of this gravitational attraction. But this is not cosmological redshift. Cosmological shift means when you have galaxies in the space and when the space itself expanding, what happens is they are cosmologically expanding. That is due to the expansion of the space itself. If I think it in like, so the galaxies are sitting on the space and everything is moving away from you, right? So the space is moving away from you. These galaxies are moving away with the expansion. And for sure, they will be redshifted because they are moving with the expanding universe. And this is called cosmological redshift. Now, the problem with the Andromeda galaxy is it's very close to us, and the gravitational blue shift that it has is more prominent compared to the cosmological redshift, because the cosmological redshift comes into play more and more when it is so far away from us, right? So that's what happens. So what happened for the Andromeda galaxy, what happens is because it is very close to us, the blue shift happened due to the relative movements of the gravity becomes more prominent compared to the amount of cosmological redshift it has. So what actually happens is when you observe it, the redshift or the blue shift that you detect from the spectrum is combination of this uh, Doppler shift, which happens to the gravity, Doppler shift, gravitational redshift, so, plus the cosmological redshift. In fact, there is another one called gravitational redshift, which I don't want to talk here. So basically, the combination of all those is what you experimentally observe. Now, for the Andromeda, what has happened was this Doppler shift, because of the relative movements come from the attraction of the gravity, becomes more prominent because it's very close to us. And that's why when you measure Andromeda, you detect a blue shift instead of red shift. But for the faraway galaxies, this Doppler shift is become less important and less become lesser, and cosmological redshift dominates. So that's why most of the other galaxies show a cosmological redshift. But actually, it's a combination of all those, right? I hope your question is answered properly. And uh, um, yes, so after few years, that could happen. There is a possibility of colliding each other galaxies, but the depending on the scales that we have, it will take a huge amount of time. But there is a possibility, yes, because it's coming towards us. Uh, How you were asking about didn't use the time dilation and the length contraction when measure the distances using Doppler effect. Uh, you can use it based on, I mean, the answer is actually yes and no. The residual velocity equation that I use, one z times c, is actually a small correction to that, these derivations coming from the time dilation equation, which I didn't use. But I mean, you can incorporate those depending on the velocities that you are measuring. Then the result will be more accurate. Actually, I didn't put those here just to keep it simple only, right? I mean, if you want it in that way, you can incorporate it, but the final result will not change that much, because I have used for redshift calculations. I have done it myself for the galaxies up to 200 million light years away. Still, V equals Z times C equation will still work without any issue. It actually comes from a little bit, mathematical, I would say mathematical approximation using the original equation. So we usually consider it, but you don't have to, do it exactly how it looks like in these relativity equations at that point. And for the larger distances, actually, these cosmological equations change quite a lot, especially for the redshift equation will be different, not this C times C. You have to consider other parameters as well. Uh, Speed of the expansion of the universe, and that's what Hubble constant tell you. I mean, right now it's around like 70 kilometers per second per megaparsec. So that's the for each megaparsec, it will go at 70 kilometers per second. Yeah, it's around that range, but there is a lot of debates about this. Some say it's 67, and I guess the latest one is around 67, 68, around that region. Um, will you see the speed of light? Um, I mean, theoretically, the furthest away, yeah, it should. I mean, theoretically it should, but I don't uh, think it will go in that way. I guess. Right. So, any other question? So, you have a question again. Someone is asking if a person pointed past situation, whole thing happened at that time. Redo this question. To be honest, not clear for me what you are asking. Uh, So this question, what happens before the Big Bang, I will leave that to you to find the answer, right? Because for our scales, we don't, you will understand at some point this is kind of what happens before the Big Bang is not something that we could answer because our time scale began at the Big Bang itself, right? Uh, Search in the web and see what happens before the Big Bang. And sorry, Madhushan, your question is kind of not clear for me to answer. Uh, this whole thing at that time, redo their pattern. Not exactly sure what you are asking about. Sorry about it. Yeah, we cannot point a time before the Big Bang. So, right. So, can we then okay, there was a question asking, will expand the universe deaccelerate? Um, there is a there are actually different models that predict what happens for the universe in the future based on something called cosmological density parameter. Uh, so there is a model that talks about it. Universe could deaccelerate, but actually we don't exactly. There is a possibility according to different models. We don't have an exact answer for this yet, I guess. There could be a possibility, but I mean, maybe. Right now, what we are knowing is the universe is accelerating. Ranudhi, I think we can finish if we don't have any questions, right? Okay, just one question there is asking space-related technologies which field I have to pursue higher studies. Uh, right, for this one, I can tell something. Let me tell about me. So what I did was I was I was doing a physical science degree and a physics special degree, and physics special degree with one or two astronomy courses will make it much easier for you to go for a PhD and select astrophysics uh, or space science if you would like, in short. But uh, astronomy is quite an interesting field that anybody who did any subject can come into astronomy at a certain point, because uh, even an engineer you can do that as well, because these technologies related to the space science are more engineering type of things. So even an engineering students, I have seen that they work a lot of space type technology. So you can there is no limitations for anyone to come into the space science technologies in that way. I think whatever you do, all you need to do is do your basic degree as best as you can. So that's what matters at the end. So that may be the short answer as the starting point. It doesn't matter whether you do engineering, chemistry, physics, whatever the degree that you are doing right now, uh, you have to finish it with the highest GPA that you can achieve, uh, which will make things easier for your next steps, because even after the PhDs, people change to the space science technologies because, for example, if you think about the NASA, they work on, different, uh, there is technology, there is astronomy, and there is a chemical side. So everyone can join into that field later. But straightforward astrophysics path will be surely a physics special degree related to, do some astronomy courses, but others can join at any point as well in that way. Uh, I mean, yeah, basically that's, I mean, in short, that's how I can explain it. Uh, where we measure that acceleration. Okay, let me get these two questions as they. When we measure that the acceleration of the universe, explain how we measure it. For the question that you have about this acceleration of the universe, I mean, that's exactly what we discussed. How we measure the acceleration of the universe is basically I think that is exactly what I have discussed in the presentation. You uh, use the Hubble plot, and you basically measure the distances and the velocities, how they are, whether they are moving away from us. I mean, how fast they are moving away from us is the basic evidence that things are moving away from us. But when you go for the further distances, you check the redshift values with the distances and compare those to understand that the universe is accelerating. Uh, Based on, I mean, if you search a little bit about that in the internet, you can probably understand it completely. Uh, because the things that you're asking is actually, it's a completely different thing to discuss about, accelerated about accelerated universe, expansion universe, basically more kind of related to the cosmological models, right? And the next question is, University of Columbia treat my future as an astrophysicist to provide. Uh, I think what I not clear this question that you have. I have got selected to the engineering faculty this year at the University of Colombo Physical Science. Are you telling that you are now in the engineering faculty and you want to, but you will change it to the physical science Colombo or and provide theory? So in short, are you now in the physical science faculty Colombo? Is it? Ah, right, okay. Uh, Basically the selection, whether you go for the engineering faculty or the physical science, it's actually you can decide what you like basically. Uh, for the Colombo, I think if you have a very special interest about go to this, astrophysics. So I mean, after physics special degree, what you need to do is, uh, um, if you are very interested, make sure that you select a physics special degree. They select, I think, large number of students in the Colombo University, as I know, and then select a project uh, from that side. If you like space technology from that side, or if it is an astrophysics side from that side. I think in Colombo, uh, there is a lecturer called Dr. Janaka. I'm sure he will probably help you with that. I know him. So he is the one I would go and talk, because I guess he will have a better knowledge to in person to instruct you what to do. Uh, Basically, what you need to do is go through the physics special degree, and once you are done with the special degree with good grades, it will be much easier. I mean, I don't know much about the other countries, but for the USA, you can directly apply for PhDs with a scholarship. They are very competitive, but still it's doable, and there are a lot of students here with that once when you apply for the physics special degree, just select a department where you have astronomy research field or astrophysics research field or space science research field. Just check the professors whether do some research in the astronomy and astrophysics, and then you can find a place to apply. Basically, what you need is only a good GPA most of the time. And there are some universities that you need some extra exams that you have to do something called graduate record examination. And for sure, you need to do an English examination, something like IELTS or TOEFL or something like that. And you will most probably get a scholarship to study. I mean, in fact, that's how I came as well. It's it's all about maintaining a good GPA and getting good grades for a special degree. And those who are actually not in a special degree just do 3 years. There are other ways of doing that as well. But I mean, if you plan a special degree, that's the kind of the shortest path to achieve things. But for the other ways, you can do as well. Right, Anudev, I think we can finish then, right?
On behalf of Setsmora and everyone here, I would like to extend our heartfelt thanks to Dr. Sandanwan Prasad for taking the time to join us today, especially amidst a busy schedule. Your insightful and engaging lecture was truly enriching, and we greatly appreciate the knowledge you have shared with us. I hope you all found the session valuable and inspiring. With that, we conclude the second session of the Cosmic Chronicles webinar series. Thank you all for joining us today. We at Setsmora eagerly look forward to welcoming you all to our next session soon. Have a wonderful night.
Right. Thank you, everyone. And thank you for inviting me.